Hi everyone, this is Arash Asghari Vaskasi from the Existential Lab at UC San Diego. Today I'm going to present active Bayesian multi-class mapping from range and semantic segmentation observations. The demand for robot operation in unstructured unknown environments such as search and rescue missions or mining has grown substantially since the last 2 decades. In order to come closer to full autonomy, robots need to be equipped with a variety of sensors which can potentially provide a rich understanding of the surrounding environment. However, a fruitful analysis of the measurement stream in real time calls for efficient sensor management strategies. In the context of robot exploration, the problem of efficient sensor management can be formulated as active mapping, where we aim to autonomously build low uncertainty maps in real time, considering the collision and visibility constraints under a limited exploration budget such as time or distance. One of the first works that attempted to propose a solution to active mapping was frontier-based exploration, which founded a family of geometry-based exploration methods. However, geometric methods generally fail to achieve low uncertainty and efficient exploration strategies due to their simple objective function. Another family of active mapping solutions utilize an information theoretic objective function, which aims to find informative trajectories that minimize map estimation uncertainty. Cauchy-Schwarz quadratic mutual information and fast Shannon mutual information, shortened as CSQMI and FSMI respectively, have been able to efficiently solve the active mapping problem, satisfying all the mentioned requirements. Here you can see a short demo of CSQMI as an exploration method. We consider our work as a member of the information theoretic family of solutions, among which our work is most related to CSQMI and FSMI. In particular, CSQMI and FSMI use range-only observation, which is used to build a probabilistic occupancy map. Their objective is to find the robot trajectory that yields the most informative range measurements with regards to estimating an occupancy map. On the other hand, our work employs range and semantic segmentation measurements, which is used to build a semantic multi-class map of the environment. Therefore, our objective is to find the robot trajectory that yields the most informative range category measurements with regards to estimating a semantic map. Our work is distinguished by using range and semantic segmentation as sensor input, Bayesian multi-class mapping as the estimation layer, and actively planning informative trajectories. Here, we state the problem in a more rigorous way. Starting with the motion model, we use a general discrete time model where xt and ut are robot pose and control at time t respectively. Also, consider Bayesian map update rule as follows, where new range category observation zt updates the previous map distribution pt-1 of m using the Bayes rule. Next, we define the problem of semantic exploration as finding a sequence of controls that maximize the mutual information between the resulting range category observations and the multi-class map, divided by the cost of the trajectory, which can be defined as distance traveled or elapsed time along the trajectory. Clearly, this optimization is constrained by the robot motion model and the Bayesian map update rule. Given the setup of the problem, we now present our first contribution. Consider a robot exploring an unknown environment. The robot is equipped with a RGBD sensor which provides a stream of depth images like here. Also, we use a semantic segmentation algorithm that detects object categories for a given input image shown here. These two images comprise our observation ZT. Next, let PTI be a categorical distribution representing the multi-class probability for each map cell, where the class 0 is always reserved for the free space and capital K is the number of object classes. Equivalently, one can express the multi-class probability using a generalized log-odds ratio vector as HTI. We show that under map cell independence assumption, one can derive this Bayesian recursive map update rule, which can be considered as the semantic generalization of the log-odds occupancy mapping. Here, LZ is a multi-class inverse observation model, which effectively encodes the information coming from the new observation that needs to be integrated to the current semantic map distribution. Now we present our second contribution. This is the general formula for the mutual information between a multi-class map and a single array of range category observation. Assuming a piecewise observation model operating over a grid representation for the map, we derive the following closed-form formula for the semantic mutual information. For detailed descriptions of P and C, please refer to the main text. Furthermore, for a sequence of feature observations, if we select a non-overlapping subset of observations, we can find the lower bound for the total mutual information as here. High-level speaking, our proposed mutual information formula aggregates all contributions from potentially visible map voxels over all object classes. In order to show why adding object classes would improve exploration, consider this simple example where the white region represents free space, the gray region is unexplored, and the colored bars represent different objects. As mentioned earlier, we maintain a categorical distribution for each map cell where the zero class corresponds to the free space. Now consider the following distribution for the map cells. Note that all three walls have the same occupancy probability, while the red walls are more certain about class 2 and the green wall is uncertain among object classes. Using an information measure solely based on occupancy similar to FSMI, we expect to see that visiting all three walls would yield the same amount of information since they have the same occupancy probability. This can be verified by obtaining the information surface for FSMI, which shows equal information for all three walls. On the other hand, our information measure is capable of capturing per class uncertainty. This is evident by examining the information surface obtained from our method. We can see that visiting the green wall, which has high uncertainty, yields larger information compared to the red walls, which have low uncertainty. These experiments hint more efficient exploration using our proposed semantic information measure. Our semantic exploration pipeline works as follows. We first identify the frontiers, we plan path to each frontier and compute the information along each path. Then we choose the path that yields the maximum information divided by the length of the path. Here is an example of semantic exploration in an unknown environment using range and category observations. As we see, the robot first attempts to find the frontiers and plan towards them. Each object has been labeled as a different color. For example, the walls are shown here as pink, or the grass is green and the dirt road is brown. As we observe, sometimes the robot tries to revisit the known parts of the map to refine its estimation. However, for the most part, the robot tries to find the unknown environments located at the frontier. We also implemented our method in a 2D simulation environment where we can compare it with other exploration strategies such as frontier-based exploration and FSMI. As we see here, on the left, we have the true map, and on the right, we have the exploration process. The robot tries to find the unknown environment while having a range measurement and classification error. Here we compare the simulation results with frontier-based and FSMI and our method. On the left, we have binary exploration where we only make use of the range of observations. As we see, our method and FSMI are on par and both outperform frontier-based exploration. This is expected since both our method and FSMI make use of uncertainty, while this is not the case with frontier-based exploration. On the right, we have semantic exploration where we also make use of category observations. As we can see, our method outperforms both FSMI and frontier-based, which further verifies the more efficient exploration using semantic information. In summary, our first contribution is to compute a Bayesian multi-class mapping update rule for range and category observations. Secondly, we have computed a lower bound for the Shannon mutual information between a multi-class map and a sequence of range category observations. These two contributions make it possible to perform semantic exploration from range and category observations. In future, we attempt to formulate the octomap representation for multi-class mapping using range and category observations. Furthermore, we try to compute the mutual information between an octomap and an observation. This is expected to yield a large-scale 3D semantic exploration strategy, which is more practical for real-world experiments. This ends my today's presentation. Thank you for your time, and I would be happy to answer questions.